In 1950, physicist Enrico Fermi, who built the world's first nuclear reactor in Chicago with the help of Leo Szilard, who also co-authored the Einstein-Szilard letter to Roosevelt, which led to the commencement of the Manhattan Project, and together with Fermi developed the world's first atomic bomb. Were having lunch at Los Alamos, where they were working on the post-war development of thermonuclear weapons. Fermi famously said to Szilard and his other colleagues, "Where is everybody?" speaking in regard to alien life. It was Fermi's view that life should have been inevitable elsewhere in the universe and should have been visible. Why had life not propagated throughout the known universe? This statement has come to be known as the Fermi paradox, even though the original statement wasn't a paradox. Fermi went on in the conversation with his colleagues to suggest that the reason we hadn't been visited might be that interstellar flight is impossible, or, if it is possible, always judged to be not worth the effort, or civilization doesn't last long enough for it to happen. Fermi's final proposition is interesting, but we'll come back to that in a moment. But much thought has been given to the so-called Fermi paradox in the decades since. In 1961, American astronomer Frank Drake created the Drake equation to estimate the number of intelligent civilizations in our galaxy. Drake calculated at least 1,000 and perhaps as many as 100 million extraterrestrial civilizations in the Milky Way alone. Last year, Adam Frank from the University of Rochester and Woody Sullivan from the University of Washington modified the Drake equation to calculate the likelihood of intelligent civilizations since the beginning of time. Their modified equation, and I'll post the link below, calculated that the likelihood that humans are alone in the universe is 1 in 60 billion. In addition to this, mathematician John von Neumann proposed in the 1950s that self-replicating robots could be used to explore the universe, the entire universe, in a period of only 4 million years. So, given the almost certain probability that life exists somewhere else in the universe, combined with the certainty that that intelligent civilization should have been able to colonize the entire universe more than adequately in the available time, Fermi's original question remains: where is everybody? There have been a number of theories proposed in response to the Fermi paradox. I'll focus on two. Many of them have flaws, which is why the debate continues. However, one suggestion is there is something called the Great Filter. The Great Filter proposes that there is some barrier to the development of civilization, the evolution of life, that prohibits colonization of the universe. Another theory posited last year by astrobiologists Aditya Chopra and Charlie Linweaver at the Australian National University is the Gaian bottleneck hypothesis. The Gaian bottleneck hypothesis suggests that, similar to a great filter, there are factors which restrict the evolution of life, create bottlenecks, slowing down evolution or forcing it to reset and restart periodically. The theory basically being summed up that life is so fragile, it never has the chance to develop adequately. So that brings us back to the three original questions. Why are we here? Why are we alone? And how long have we got to live? The answer to these three questions, and the point of this video, is surprisingly simple. Physics is very complex and not yet well understood in many areas, but chemistry is pretty straightforward. We spent 2 centuries, thereabouts, identifying and classifying all of the elements in the periodic table. We've mapped all of the structures and properties of the elements, and all these tiny numbers in the periodic table represent those structures and properties. All of these elements have unique characteristics, but there's one element in particular that is very, very special. The existence of which in the universe answers all of our biggest questions. Diamonds, sugar, oil, coal, natural gas, charcoal, plastic, graphite, limestone and marble, radioactive dating of prehistoric artifacts, greenhouse gases, methane, chlorofluorocarbons, and hydrochlorofluorocarbons, carbohydrates. All of these things have one element in common. All known life on Earth is based on carbon molecules. Every plant, every animal, every insect. There are more than 10 million organic compounds based on carbon that chemists have identified. What makes carbon special is the 4 valence electrons that allow it to form multiple bonds with other elements. Its small size, it is compact enough to form very dense, very complex compounds. It's also the 4th most common element in the universe. That abundance is important. While there are other theoretical biochemistries that have been proposed, many of them are limited by the fact that the elements involved are not very common. And lastly, it has a very high melting point, so it's thermally stable as planets form and cool. It isn't flipping in and out of solid, liquid, gaseous states at the kind of temperatures that are necessary for the formation of life. If you rank all of the elements in the periodic table by the availability of multiple electrons to form bonds with other atoms, being its valency and its atomic radius, being its ability to fit into compact, complex molecules. Thirdly, its attractiveness to other elements, using the Pauling scale of electronegativity. You could use bond length for a number of other proxies, but the results are the same. Fourth factor being abundance in the universe and thermal stability, the high melting point. Carbon is a standout. You could come up with a formula for calculating the overall suitability of elements for the formation of life, but then you start making assumptions about how life forms and the conditions in other ecosystems. So if you simply rank carbon compared with all the other elements, it comes 33rd on valency, the valency of 4. It comes 10th on atomic radius, 12th on electronegativity, 1st on melting point, and 4th on abundance. If you multiply all these properties, no other element comes close. So of all the elements in the known universe, carbon has the best combination of ability to bond with other elements, suitability for forming complex molecules, is thermally stable, and is readily available. 2 years ago, mathematician Jeremy England, 31-year-old assistant professor at MIT, derived a mathematical formula that shows that if you take carbon in the presence of other common elements, oxygen and hydrogen in particular, and shine sunlight on it, the resulting compounds will inevitably form complex proteins and then cells to dissipate heat, based on the second law of thermodynamics. So life is actually inevitable. It's an inevitable product of the fact that carbon exists in the universe. The minute in the Big Bang that matter organized into the periodic table that we have, and carbon formed as one of the elements, it was only a matter of time before carbon, oxygen and hydrogen arranged into the complex molecules that form life, based on dissipation of heat. So that's the answer to the first question, why are we here? We are the inevitable product of carbon in the universe as an element, forming complex compounds and proteins and cells and life. But there's a twist. If life is inevitable, then where is everybody? The answer to the second question, why are we alone, is actually the same answer as the first question. The same properties of carbon that make it the key ingredient of life also make it the primary cause of mass extinctions. And we don't have to go very far to look for a practical example. Our twin planet, Venus, our solar neighbour, has all the same properties as Earth, is roughly the same size, shares a similar chemical composition, and orbits the same sun. By any logic, life should have evolved on Venus in the same way that it evolved on Earth. The problem is the atmosphere on Venus is 96.5% carbon dioxide. Venus's carbon is trapped in the atmosphere. There have been several near-miss mass extinction events over the last 3.5 billion years that life has been evolving on Earth, all worsened by concentrations of greenhouse gas in the atmosphere. but mostly triggered by the Siberian traps and Deccan traps, geological activity, or meteor strikes. The difference now is that the extinction event that we are now entering has been caused by anthropogenic or human CO2 emissions. But throughout that 3.5 billion years, all those billions of species and millions of generations and iterations of various life forms have all ultimately ended up in the ground as oil, coal and natural gas, fossil fuels. Now, for human civilization to develop to the point where we are now, including advanced manufacturing, space travel, and the ability to put satellites into orbit to monitor our conditions, the development of computing and the complex processing of information that has enabled, all were only possible because of the use of fossil fuels. Human civilization had to access energy sources to develop to the point where we're now aware of our predicament. So before intelligent life can even emerge in an ecosystem, there's already fossil fuel in the ground: coal, oil, natural gas. So the minute that we first started burning wood 125,000 years ago and harnessing fire as an energy source, we effectively set the clock running on a doomsday clock for our own extinction. We moved from wood to coal to oil and natural gas, always combusting the carbon, which is the remnants of our evolutionary ancestors. The same carbon that once formed life, and in increasing volumes. We can now even trace the isotopes of carbon, namely carbon-13, in the atmosphere as one of the proofs that the carbon we've burned is causing global warming. Given the inevitability of life and of greenhouse gas emissions and global warming, it is almost impossible that we are the first civilization ever to have faced this challenge. Any carbon-rich ecosystem is equally prone to propagating life and suffering runaway global warming. And every life form that ever existed anywhere in the universe would ultimately have faced the same dilemma. The minute we sent that first whiff of smoke into the sky, we began to seal our own fate. As we dig for coal and oil, we are literally digging our own grave. Once CO2 levels in the atmosphere reach a tipping point at around +5 degrees from where we are now, as we saw during the End-Permian Gaian bottleneck, rising ocean temperatures then trigger the release of deep ocean sediments called clathrates. These kick the temperature up another 20 degrees, and the last time this happened, 95% of life on Earth went extinct, a Gaian bottleneck. The only way the temperature ever came down again is that enough algae survived in the oceans after that event to slowly reabsorb the carbon. Otherwise, the Earth would now look very much like Venus, hundreds of degrees hotter and devoid of life. And so this answers our second question: why are we alone? The presence of carbon not only propagates life, it is also a Gaian bottleneck through mass extinction events, slowing down the evolution of life, and ultimately leads to the extinction of all life. The Great Filter. The faster that a civilization develops, the more that it accesses those fossil fuel reserves, the faster it leads to its own extinction. And hence the absence of intelligent life elsewhere in the universe. Both mutual properties of carbon. Just as inevitable as life is extinction, both owing to the properties of the same element. Which leads us to our third question: how long have we got to live, and what's our future? In 1964, Soviet astronomer Nikolai Kardashev developed the Kardashev scale, classifying intelligent civilizations into 3 categories based on their energy sources. Human civilization is currently forming type 1 civilization, being as we rely on fossil fuels. So, for any civilization to move to type 2, to travel the stars and begin to propagate throughout the universe, it must abandon the combustion of carbon as an energy source. And that's the carbon paradox. The same reason that we exist is the reason we have not yet encountered life elsewhere in the universe. Life, to achieve intelligence, must survive both Gaian bottlenecks and ultimately the great filter of global warming. Our species stands at a crossroads. At the same point in Earth's history that we've become aware of our predicament, it's almost too late to stop it. Will we develop the technologies and the governance structures to regulate carbon, combustion of carbon and greenhouse gases in the atmosphere, and manage Earth's atmosphere? If we don't, we may disappear without a trace, taking all known life in the universe with us. If we do, we can use that same capability to control temperature in the Earth's atmosphere in future Gaian bottlenecks, be it geological activity or meteor strike. Equally, we could use that same capability to manage the atmospheres on future worlds. We may well be that species that explores the entire known universe over the next 4 million years. And so the answer to the third question, how long have we got to live and what is our future, really depends on that choice.